Okay, so when you're going to talk about the Haber process is basically the process that you use when you want to make ammonia, right? So you have your ammonia gas, and to make the ammonia gas, the process you use is known as Haber process. So Haber process is an industrial reaction, right? And it is actually reversible reaction. So everything is single thing, you've studied about reversible reactions, everything that we have talked about, you can go ahead and apply it to the Haber process. So ammonia has a lot of different uses. You can use it as an alkali, you can use it in your detergents, you can use it in bleach. So ammonia is something that is really often used. So we need a way of being able to make huge quantities of it. And to be able to make huge quantities of it, we have now come up with an industrial process that has the best possible conditions. Okay. So first of all, let's discuss what the process actually is, and then we will relate it to the topic of reversible equations. So when we talk about ammonia, we need two things. We need two products. I mean, two reactants. Okay. One is nitrogen and one is hydrogen. These are the two things that we need to be able to make ammonia. How can we obtain ammonia? Nitrogen. How can we obtain nitrogen, right?
From
So
the
the
air.
way, yeah, from the air, exactly. Do you know what process we use to obtain it from the air?
Um, no.
Okay, the process we use is known as fractional distillation. Okay, it's over here. Fractional distillation. This is the process that we use where we actually separate nitrogen from the other components of the air. Now, fractional distillation is a process that allows you to separate the components based on their boiling point, right? Based on the boiling point, you can go ahead and you can separate the different components. This is a process that we generally use. Okay, this is a process that do I have a diagram? This is the process that we generally use when we have got a mixture of gases or a mixture of liquids, right? So in this situation, what we basically do is we cool down the air until it turns into a liquid. Once it turns into a liquid, what we do is that we go ahead and we perform the process of fractional distillation. So all of your gases, they have a different boiling point. So you put them in a sort of a fractionating column. You have a tower like this. And inside the tower, there are areas of different temperature. So normally at the bottom, you have high temperature, and then at the top, you have low temperature. So what happens that you put the liquid air, so you cool down the air. You take it all the way to minus 200. You cool it down until the air turns into a liquid from a gas. Okay. And after that, what you do is you put in the column. Now, in the fractionating column, every area has a different temperature. So for example, the area of the column where the temperature matches the boiling point of nitrogen, in that area, nitrogen will end up collecting because it is matching the boiling point of nitrogen. The other components will keep on moving up the fractionating tower. So based on the boiling point, we can separate the components from each other. So you'll do the entire process. This is in your Excel syllabus. So I don't know if you will do it this year or if you'll do it next year, but it is in your syllabus. So you'll study the entire process in
We just
detail.
learned like how to do it. We just learned like how to do it,
Mhm.
what temperature it is, what atmospheric pressure it is on.
Yeah, yeah. And you will use this. So when you will study organic chemistry, so in organic chemistry, when you talk about crude oil, okay, you must have like heard generally
Yeah,
as
they'll
well.
be separated by this
Yeah,
fraction
exactly.
distillation.
You separate them by fractional distillation, and you have a topic known as separating techniques. So in those separating techniques, one of the techniques we use is fractional distillation. So you will the basic concept of it is that you're separating it based on the boiling point, whatever is the boiling point of nitrogen. based on that, you're separating it from the other components, right? So this is the entire process. I'll just go over it with you. I have not seen questions related to this. So, but I'll still go ahead and go over it with you. So generally, first thing you do is that you first pass the air through fine filters to remove dust. So whatever dust is present, you are going to pass the air through fine filters to remove your dust. After that, the air is going to be cooled down to minus 80 degrees centigrade. First, you'll cool it down to minus 80. Why is that? Because you want to remove water vapors and carbon dioxide. So at minus 80 degrees centigrade, the water vapors will turn into ice and carbon dioxide will turn into a solid as well. So you simply go ahead and you remove these. If you don't remove them, then what will happen? That these solids will then block the pipes and it will affect the process. Then you are going to compress the air at about 100 atmospheres. So first take it to minus 80, remove your solids, then compress it to about 100 atmosphere of pressure, right? What happens that when you compress the gas, whenever you
Pressure
increase the pressure,
increases, so rate of reaction increases.
uh, technically over here, you're not doing a reaction because you are just have one reagent, air, right? All you have is air. So what actually happens is that when you increase the pressure, temperature increases. So the air becomes warm again. So then you have to again cool it down. You again have to bring the temperature down. And you keep on doing it. You keep on cooling the air, then compressing it, then cooling it again, and then compressing it until the temperature falls down to minus 200. At minus 200, now all of the components of air or majority of the components of air have turned into liquid. Then you transfer them into a fractionating column and you do fractional distillation, separating the different gases based on their boiling points. So by using this particular method, you get nitrogen. I have not seen any question where they ask you details of this process. I have told it to you just in case it comes in your exam, but in your Excel past papers, I've never seen a question where they've asked you details of the temperature and pressure for this process. Okay, they do ask you for the Haber process. Haber process is very important. You need to know all the details related to this, but generally they ask you how you obtain nitrogen, and if you write down fractional distillation, that is enough. They give you marks for that. So fractional distillation is how you will get your nitrogen. For hydrogen, what you do is you do a process known as steam reforming. So hydrogen can also be obtained, by the way, from liquid air. Okay, so by doing fractional distillation of liquid air, you can obtain hydrogen from there as well. Okay, another way you can obtain hydrogen is by doing a process known as steam reforming. The process is very simple. You take your methane, that is an organic compound, and you react it with steam. The products you will get are hydrogen and carbon monoxide. Okay, so this is how you can obtain the process as well. But generally, you can get it in a similar manner. You can get it from fractional distillation of air. Now, once you have obtained your entire once you have obtained the entire thing, you have to go ahead and you have to actually perform the reaction. So first of all, you have to remember the conditions, okay? We do it around 200 atmospheres, okay? And the temperature is between 350 and 500 degrees centigrade. So 350 degrees centigrade, 500 degrees centigrade, and the temperature is approximately 200 atmospheres. Now, what you do is that, hold on, have I mentioned the right, and the when you are going to talk about it, the one second. Right. So the pressure you use is between 200 to 400 atmospheres, and the temperature you use is between 350 to 500 degrees centigrade. Okay, these are the conditions that you actually have for your reaction. The catalyst that we use is iron.
Iron.
Okay.
Yeah.
Yes, so you have to remember these three things. The catalyst is iron, and this is the temperature, and this is the pressure. Now, what you are going to go ahead and do is you're going to take your nitrogen and hydrogen, and it will give you ammonia. Now, first of all, let's talk about our entire concept that we studied in reversible reactions. So, first of all, what is the effect of increasing the temperature? This is an exothermic reaction. So,
Yeah.
if I will increase the temperature, the reaction will go to the side that is endothermic. So that means the reaction
Backward.
is going to go exactly backward. So in this condition, low temperatures are favorable, right? Lower the temperature, the better your process is going to be. Secondly, what is the effect of pressure? If I increase the pressure, the equilibrium will shift to the side with less number of molecules. That is towards the right hand
So there
side.
would be constant, like there will be no, it won't go to any side.
It will go to side Aram, because over here you have 2 and over here you have 4. 3 plus 1 is 4. So over on this side, the right side, you have 2 of ammonia. On the left side, you have a total of 4, 3 of hydrogen and 1 of nitrogen. So when you will increase the pressure, the reaction will go to the right side. It will go towards the ammonia. So when you increase the pressure, the amount of ammonia is going to increase. Okay. Now, what they go ahead and they often ask you is this. So they will give you questions like this. They will basically say that, okay, so higher the pressure, the more ammonia is going to be produced, right?
Yes.
They are going to go ahead and say that why can we not use more than 200 atmosphere, or why can't we take it up to 700 atmospheres? Why can't we take the pressure much higher to produce as much ammonia as possible? Because it makes sense, right? If pressure is increasing, amount of ammonia, keep on increasing the pressure. But
Yeah.
we have to realize that increasing so much pressure is a very, very expensive process, right? We are doing this on an industrial scale, so we have to think of a way to keep it economical. Otherwise, the process will become too expensive. So eventually, this is the pressure that they ended up agreeing on, that around 200 to 400 atmosphere is the pressure at which we are going to work. It is enough pressure that we are getting a good amount of ammonia, but not so high that it would increase the cost of the process. So they ask you, why are we not using a higher pressure? So generally, the higher pressure you use, the more costly your entire thing is going to be. Secondly, they will ask you about temperature, that lower the temperature, the greater the amount of ammonia produced. So why not lower the temperature? Why are we keeping it to 350? Why not go to 100 degrees centigrade or 10 degrees centigrade or 0 degrees centigrade? Because at lower temperatures, the rate of reaction becomes so slow that it is again no longer feasible. The rate of reaction falls down so much. So as you lower the temperature, you are getting more ammonia, but the rate, the speed at which you're getting the ammonia, that will fall down. And that falls down, and eventually what's going to happen, it's no longer going to be feasible, because it's going to take too long for you to get ammonia. You might get more ammonia, but it will take too long to get it. So eventually 350 to 500 degrees centigrade was the temperature at which the rate of reaction was fast enough, and we were still getting a good amount of ammonia. So that is what they ask you, that what is the effect of temperature, what is the effect of pressure. So why don't we increase the pressure further? Why don't we decrease the temperature below this? So
Yeah.
that is how you're going to explain it, that too much pressure means extremely expensive, extremely high cost. Too low of a temperature means rate of reaction is too slow. And again, so this is the sort of the balanced pressure and temperature at which we are getting enough of a result, right? And when you're going to talk about this entire concept, so generally this okay, so this entire theory that you have studied, that I've taught you about pressure and I've taught you about temperature, okay, this is known as the Lee Chatelier principle. I'm just letting you know in case it comes with, they ask you by name. explain the Le Chatelier principle. Okay.
Reversible reactions, right? Or
Yeah, reversible reactions.
okay.
The reversible reactions, the effect of pressure and temperature on reversible reactions, that is the Le Chatelier temperature, Le Chatelier principle. And basically what the principle states is that, so I told you, higher the pressure, the equilibrium will shift to the side with less number of molecules. Why will it go to the side with less number of molecules? Because you want to restore the pressure back to its normal value, right? You want to restore the pressure back to its original value. So to do that, to bring the pressure back to an equilibrium value, the equilibrium shifts to the side with less number of molecules. When there will be less number of molecules, there will be less collisions of the particles with the walls of the container. As a result, there will be less force exerted per unit area, so pressure will decrease. So you will restore the pressure will decrease. That is why the pressure shifts to the side with equilibrium shifts to the side with less number of molecules. If the pressure drops, now you want to increase the pressure back to normal. So in that situation, it shifts to the side with greater number of molecules. Greater number of molecules will have more collisions per unit area, so more force per unit area, so pressure increases. And then they ask you to explain the logic of temperature as well. So in temperature, basically what happens is that when you increase the temperature, the reaction shifts to the endothermic side. Why? Because you want to restore the temperature back down to the normal value. So if you want to restore the temperature down to a normal value, you have to reduce the amount of heat being produced. How can you do that? Shift to the endothermic side, because in an endothermic reaction, heat is absorbed. So the increase in temperature, whatever temperature has risen, whatever heat is being produced, the reaction goes to the endothermic side. It absorbs all of that heat that is being produced. Temperature drops down back to the original value. Same is true for the opposite. When temperature is going to be too low, what will you do? You will go to the exothermic side. The exothermic side will start to produce your heat, right? The exothermic process will start to produce heat, and that heat is going to again bring the temperature up to normal. So this is all related to your Le Chatelier principle, and this can be applied to your Haber process, right? Making sense?
Yes. Yes.
Okay, so generally what you do is that we normally get around 15% ammonia. Okay, after we have obtained our ammonia, we will cool it down and we will condense it into a liquid, and we remove it from the reaction. Whatever nitrogen and hydrogen was left behind that did not react, you can just recirculate it. You just put it back into the reaction so that they can undergo further reactions. So that is one good thing, that you are being more economical, because you can reuse the unreacted nitrogen and hydrogen in the process. Okay.
Okay.
So how much ammonia do we get? We generally get around 15% ammonia from the entire mixture. And as you know that the since this is a what do you call it, reversible reaction, so there will be dynamic equilibrium, and the conditions for dynamic equilibrium are pretty much going to be the same. Now, when we talk about ammonia, let's quickly go over the properties of ammonia, because we have discussed it, and how you will test for ammonia, because that is important. Okay. So ammonia is first of all a colorless gas, right? It is less dense than air. It is less dense than air. Okay. It has a very sharp and pungent smell. So it has it is actually one of the ways by which you can recognize that what you're smelling is ammonia, because the smell is so pungent. It creates sort of a choking feeling, you know, when there's a gas or an odor that's so strong, it literally makes you feel like you're choking. So ammonia has a very strong and a very pungent smell. It is actually one of the tests that helps you recognize that you're dealing with ammonia. And ammonia is very soluble in water. Ammonia can dissolve in water to give you ammonium ions. Okay, that
And
is
it,
how ammonia sorry.
Ammonia is NH3 and ammonium is NH4.
NH4 plus, because it turns into an ion. So ammonia will dissolve in water to give you a weakly alkaline solution. Ammonia gives you a weak alkaline solution. So it will be a reversible reaction because it is a weak base. Okay. And why is it a weakly alkaline solution? Because it is giving you a low concentration of hydroxide ion. So the ammonia is binding with the hydrogen ions from the water. So the water is breaking down into hydrogen ions and OH minus ions. The hydrogen ions are combining with ammonia to give you NH4 plus. These hydroxide ions are then available in the form of an alkaline solution. So it leads to production of a low concentration of hydroxide ions. That is why it is a weakly ionizing solution. Okay. So when you're going to talk about it, hold on. Um, we don't have to do any of this. Okay. So when you are going to go ahead and talk about it, generally the test we have for ammonia is that we can go ahead and use our litmus paper. Okay. So I just told you that we have our ammonia is a weakly alkaline substance. So what we can go ahead and do is that we can first thing is that it will give you a very pungent odor. Secondly, you take a red litmus paper and you will dampen the red litmus paper. Okay, you will dampen it. Why? Because this is gas, so you need to damp it so the gas will react with it and give you ammonium ions. So when ammonium ions are going to be produced, what is going to end up happening? The red litmus paper will turn blue. So that is another test that you can do to test for the presence of ammonia ions. So basically that was all you have to know relating to Haber process. So I think the just the Haber process is coming, right?
Yeah.
And nothing else related to the rest of the topic is coming.
No.
Okay, all right. So, okay, now let's go ahead and take a look at a few questions because there were questions in our topics that we left in the middle because they were related to Haber process. So now we can go ahead and actually go over them. Just give me 1 minute. I'll share the screen with you. Okay, you don't have to do the topic related to formation of your fertilizers, right?
No, I don't think so.
Yeah, okay. Okay, all right. Because the ammonia that you get at the end of it, you can use this ammonia to actually make your fertilizers. That's why I was asking you. Okay. So
Okay.
I will, yeah. So they, when you are taking a look at the questions, you are going to find questions over there for this as well. They ask you related to your fertilizers. So that's why I was asking, but I don't think you have to do that because you don't have to do the entire topic. Okay, let's go ahead and take a look at this question. Okay, the first thing they're asking you is when nitrogen and hydrogen react to form ammonia, the reaction can reach a dynamic equilibrium. Explain what is meant by dynamic equilibrium.
And dynamic equilibrium is when the rate of forward reaction is equal to the backward reaction, and when the concentration of the substances are same or
Yes.
that.
Yeah, the concentration, basically the concentration of the product and the reactant does not change,
Okay.
right? Remember, they're not equal to each other. Don't say that the concentration of product and reactant are equal. They're not. They just don't change. At dynamic equilibrium, the concentration of the product and the reactant will remain the same, whatever they are. Okay? They just don't increase or decrease, they
And
remain the
then the
same.
reaction still continues
Yeah,
also.
the reaction still continues because it's going at the same rate. So the concentration of the product and the reactant remains the same. It does not change. But they're not equal to each other. And the third thing you can say about a dynamic equilibrium is that the forward reaction and the backward reaction occurs at the same time. In industry, the reaction between nitrogen and hydrogen is affected by the conditions used. The pressure used is 250 atmospheres. Explain how use of a higher pressure would affect the equilibrium yield of the ammonia.
Um, when we use higher pressure, like as the pressure increases, the equilibrium is shifted aside by lower molecules, which is ammonia. Hence more ammonia would be produced. Hence, the yield of ammonia will
Yeah,
increase.
exactly. Good job. And the temperature between nitrogen and hydrogen to form ammonia is exothermic. The temperature used is 450. Explain how the use of a lower temperature would affect the equilibrium yield of ammonia.
Lower with the reaction. Yes.
You can take it. Yeah, go on.
Okay. As we decrease the temperature of the reaction, the equilibrium will shift to the backward side, like the endothermic reaction.
Yes, good.
Less so less so less ammonia will be produced.
So less ammonia will be produced. Good job. Even at 450 degrees centigrade, the reaction is very slow. State what is used in the industry to overcome this problem.
A catalyst.
A catalyst, iron catalyst. Good job. Calculate the minimum volume of hydrogen required to completely convert 1000 dm cube of nitrogen into ammonia. So you have got 1000 dm cube of nitrogen into ammonia. What is the minimum volume of hydrogen gas? What is the minimum volume of hydrogen gas you need to convert 1000 dm cube of nitrogen into ammonia?
Can I see the question?
Yes, of course. Here you go. Let me know if you want to scroll up.
A 1000 dm cube of hydrogen.
Are you sure? This is the
Or
equation for the equation reaction. Oh,
wait, wait,
but
wait.
make sure you learn the equation for the reaction as well.
Okay, then I think 3000 because you multiply.
3000. Exactly.
Yeah.
Because the ratio between them is 1:3. So you need 3000. Now they're saying ammonia is reacted with excess nitric acid to make ammonium nitrate. So this is basically an acid-base reaction, okay? So nitric acid is the acid and ammonia is the base, and it's giving you your salt. Calculate the mass of ammonium nitrate produced by the complete reaction of 34 grams of ammonia.
Ammonia. Mm. How would we find the mass
Mhm.
of ammonium nitrate? Like I found the mass of 1 mole, but the mass.
Of ammonium nitrate, use
Yeah.
mole ratios. Look, you have the mass of ammonia. You can use the mass of ammonia to find the moles of ammonia. And then using mole ratio, you can find the moles of ammonium nitrate and then use the formula to find the mass. So this is a moles question, right? So they have given you information about ammonia, use ammonia.
Okay, we
Find
have
the,
to compare it with what? Like
you
the
have the ratio. What is the ratio between ammonia and ammonium nitrate?
1:1.
Right. 1:1. So that means whatever are the moles for ammonia, the moles for ammonium nitrate will be the same, right?
Yes.
So that's what you will do. Find the moles of ammonia. The moles of ammonium nitrate will be the same. So put them in the formula and find the mass of ammonium nitrate. So exactly the same. This is an acid-base sort of a question. So in acid bases, like we practiced, just like that, you will solve this question.
Okay. 2.
2 is the number of moles. Now you
Yeah.
have the number of moles. Now calculate the mass of ammonium nitrate.
Um,
Same
it will
formula,
be
use
160. 160.
160. Good job.
Um,
Exactly 160. So you will just calculate the mass of 1 mole of ammonium nitrate, right? So nitrogen is 14, hydrogen will be 1, and oxygen is 16. So you just find the mass of 1 mole, multiplied by 2, you will get 160. So the mass is 160. Okay. Okay. This is contact process. That contact process is also part of, also is a reversible reaction, but that is not coming right now. So we are not going to go over it. Now, take a look at this question. This is what I was talking to you about. The reaction between nitrogen and hydrogen is exothermic. Okay. If nitrogen and hydrogen were reacted at 150 atmosphere pressure and 300 degrees centigrade without the catalyst, some ammonia would be produced. In Haber process, a pressure of 150 atmosphere and a temperature of 450 are used in the presence of iron catalyst. Explain why the conditions used in Haber process are better than the first set of conditions for the manufacture of ammonia. So this is a 6-mark question, okay? So take your time, make sure you mention all of the details. It has to be a proper answer. You mention all of the details. You have to tell me why this is better than this. Why is the condition of Haber process better than what they have said above? Okay, you have to talk about pressure. You have to compare the pressure, the effect of temperature, and the effect of catalyst. All three things you're going to have to go ahead and discuss. And say six mark questions, so make sure you're mentioning all points. So go ahead, Aram, take your time. If you want, you can write it down on a piece of paper and send it to me, or if you want, you can type it over here in the chat, our Zoom chat. So you can type it over here and I can look at it, or you can do it on a piece of paper, whatever you prefer. So write down a proper answer like you write down in an exam, and then we will go ahead and discuss it.
So catalyst, pressure, and temperature.
Yes, catalyst, pressure, and temperature. So what is the effect of it and why we are choosing it, right? What is the effect of 400 degrees centigrade and why are we choosing it? You have to justify it too.
One minute, miss. We can't use a catalyst, right? Because it will reach dynamic equilibrium. Or
The catalyst will not have any effect on the position of the equilibrium, right? But it will have some effect if you remember.
it will have little effect, but not that much effect,
Not
right?
on the position of equilibrium. Yes, it will have no effect on the position of the equilibrium.
I sent.
Okay, all right. Let me go ahead and take a look.
I sent it in the chat.
Yeah, yeah, I got it. Here we go. So let me go ahead and see what you've written. Okay. Since the reaction is exothermic, means that it gives us heat. Specify. Since the forward reaction is exothermic, okay, make sure you always specify which reaction you're talking about. It gives out heat, so an increase in temperature would result in the reaction shifting to the left side or to the endothermic side. So the yield of reactants will increase. Good. And the yield of ammonia will decrease. So
Okay.
now you have said this is completely correct. The question is asking you, why is it better to use 450 over 300 degrees centigrade? Okay, that is what they're asking you. They're saying, explain why the conditions used in Haber process are better than the first set of conditions. How will you explain this? So according to what you said, the yield of ammonia will decrease. So why is it better to use 450 degrees centigrade
Because
over
it's more
300
than
degrees?
300 degrees
Sorry?
pressure. I mean, higher temperature because it's
Yeah,
high.
so higher temperature is decreasing the amount of ammonia. So why is it better? That's what they're asking you. Why are the conditions of this is the condition of the Haber process to use 450. So why are the conditions of the Haber process better than what they said above? So why is it better to use 450 when 450 will increase the amount of ammonia? So why is it better to use it?
So it's
That is
like
what they're
because more like ammonia will be produced. Like that's the reason of this reaction.
not that more ammonia will be produced. Okay, it is basically when you're going to talk about it, this you have to link to rate of reaction. So even though, so at 4 but so at 450 degrees centigrade, the yield of ammonia is decreasing. But at the same time, what will happen? But at the same time, the rate of reaction will increase. That is why, even though at a high temperature, at 450, we are getting less ammonia, we are still preferring it over 300 degrees centigrade. Why? Because even though we are getting less amount of ammonia, we will get the ammonia faster because the rate of reaction will be faster. Remember, that is what I told you. Why do we not take it down to room temperature? Because we said it, lower the temperature, the more ammonia you get. So it makes sense. Do it at room temperature. You don't need to heat it up. You don't need to do any energy. Don't need to put in any heat energy, and you will get a bunch of ammonia. But the lower the temperature, the slower the rate of reaction. So you will get more ammonia, but that reaction will take a very long time. And that is the logic over here as well. Even though 450 is giving us less amount of ammonia, but the rate of reaction is going to be much, much faster. And then you have to explain why. So increase in the temperature will increase the kinetic energy and
Of the
the,
particles.
yes, number of collisions. So there will be more successful collisions, and the molecule, and also a greater number of molecules will have the activation energy.
Energy. So
Exactly.
basically,
So
the increase, like this is that
yes,
answer where from the rates of reaction will answer, right? Why increase the
yes.
temperature?
Yes, exactly. So you are going to say that even though your react the amount of ammonia produced will be low, but the rate of reaction will be higher. That is why we are going for 450 degrees centigrade, because the rate of reaction is higher. So this is where you had to mix both the topics: rate of reaction, and your equilibrium. So now you've talked about both the things. Just like that. So these are the points that you're going to talk about related to your which is basically going to be your what do you call it, temperature, right? So in temperature, you have to talk about at higher temperature, what will happen with the equilibrium, and at the same time, the rate of reaction. So the rate of reaction will increase, but the equilibrium will go towards the left side. So the ammonia is going to, you will get less ammonia. Okay. Then when you've talked about pressure, you are going to, for pressure, you have said the right thing. So pressure is the same in both of the conditions, right? So you can just simply mention that the pressure is same in both of the conditions. Since we're not changing the pressure, the equilibrium will basically stay where it is, right? Pressure will not have any effect as such, simply because the pressure in the Haber process and above, they are the same. They're both doing it at 150 atmospheres. So pressure will not really have any effect. Then when you've talked about iron catalyst, again, you have said that it will have no effect on the position of the equilibrium. You are going completely correct. But you again missed an important point. That is that even though it will have no effect on the equilibrium, it will have an effect on the rate of reaction. That is why we add a catalyst. Why are we using a catalyst in Haber process?
To
Because it
increase
will
the rate
not,
of
sorry,
to increase the rate of reaction.
rate of reaction. Exactly.
Okay.
That is why we are using it, not to produce more ammonia, to increase the rate of reaction. And again, you will explain over here, catalyst will lower
The
the
activation energy
required activation energy. Good job. Which will lead to more successful
collision
collisions. So the rate of reaction will
will
increase. So you will mention both points. Over here, you have to talk about the rate of reaction and your equilibrium. So you are completely right on the equilibrium. It is not going to have any effect, but it will have an effect on the rate of reaction of both the forward reaction and backward reaction. So the rate of reaction will increase for the forward and the backward reaction. So it affects both. It affects both equally. It will increase the rate of reaction of both. So it will speed up the forward reaction and it will speed up the backward reaction as well. So both of the reactions are going to speed up at the same time. Okay, so this is the points that you had to add over here. Okay, so when I was discussing it with you in the while I was telling you about the theory, so I said this is what they ask you, that if it's better to have a low temperature, then why are we doing the reaction at a high temperature? So then you have to explain it by saying that at a low temperature the rate of reaction is too low. That's why even though low temperature gives us more ammonia, we need to do it at a higher temperature, because the reaction will be too slow, and you will simply just, it will take you too long to get that ammonia. So it's not, think of it like in a business manner, it's just not feasible. You're spending so much money, it's taking too long. You might get more but it's just not worth it because it takes too long. So that is why, even though it is better to do it at low temperature, we do it at a higher one, because we might get less ammonia, but we'll get it quickly. Same is true for pressure. Higher the pressure, the more ammonia we will get. But in pressure, the cost that you will have to deal with, the procedure is going to be so expensive that it will just not be worth it to give that high pressure just to increase the amount of ammonia. And that is why we use a catalyst, even though it has no effect on the rate of reaction. Okay.
Okay.
So, sorry, it has no effect on the equilibrium position. So that is how you're going to answer these related questions. Okay. Okay. Hydrogen reacts with oxygen to form water vapor. If 200 centimeter cube of hydrogen react completely with 100 centimeter cube of oxygen, what is the maximum volume of water vapor formed if all volumes are measured at same temperature and pressure? So this is again related to mole calculation. So I want you to practice mole calculations because you get them in your acids and bases.
Okay. If 100 centimeter cube.
Hmm? Did you get the answer yet?
One minute, I was thinking.
Good, no problem.
I cannot figure it out.
Okay, it will be 200 centimeter cube. Look at the ratio between hydrogen and water. It is 2 is to 2, right? Basically, it is 1 is to 1, right? I mean,
Yes.
if I cancel it out, it will be 1 is to 1. So that means the moles of hydrogen will be the same as the moles of water. So over here, it will be the same, because when you are using the formula for gas, the mole formula of gas, you use mole is equals to 200 upon 24, right? That is what you do. So you will do 200 upon 24 to get the number of moles of hydrogen. Okay. So that is just going to go ahead, and if I do that, 200 divided by 24, I will
Why
get 8.
24?
That is the formula. N is equals to volume divided by 24.
EMQ.
24, 24 dm cube, exactly. So that will be 8.3. So the moles of hydrogen are 8.3. The moles of water will be the same because they have a ratio of 1 is to 1. This will also have 8.3. So apply the same formula again. N is equals to volume upon 24. So again, your moles are the same, 8.3. So you again multiply by 24, you will get the same volume, 200. So in situations where using this formula, you can generally convert the volume directly. So you will end up with 200 centimeter cube of water. Got it?
Okay. Yes, thank you.
All right, Aram will go ahead and we'll stop it over here for